Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi, students. So we continue with our discussion of rotation. Okay. So there are many important ideas here, and I want to make sure that these are well understood. You know, um, and when it comes down to it, that you will all be able to solve the problems involved. Okay. Uh, so in the context of rotation, right, uh, there are the basic questions that we ask about what is the dynamics of rotation and the statics of rotation, right? We all know Newton's second law and the idea of mechanical equilibrium, right? So, the idea of mechanical equilibrium involving Newton's second law is dp by dt equals zero, right? And sigma fi equals zero, right? And if there is no external force, then you have, the condition for translational equilibrium, right? Now, translational equilibrium, right, is a necessary condition for as well. Okay. Now, if there is translational equilibrium, right, it is still possible for there to be rotational dynamics. Okay. Now, if there is total equilibrium, then there is both translational equilibrium and rotational equilibrium. Okay. Now, if there is translational equilibrium, the sum of the forces is zero. Now, but it is possible that the center of mass of a body is either stationary or it is rotating. Okay, or the body is rotating but the center of mass is stationary, right? So that is the important idea there. When is something rotating? It's rotating if there is if one, there is some kind of torque on it, right? And two, if there is a continuous force towards the center. Okay. So now if you have some kind of torque, what does torque do? What is, in some ways you can think of torque as something that produces rotation, that is, that forces something to, there's an unbalanced force. Okay. Now, when you have a propeller, it is hinged, right? And you push it this way, right? You notice that it rotates but it does not move. There is still translation equilibrium. That means that the force at the center and the force at the edge cancel each other. Okay. Now the force at the edge produces, in addition to just being a force, also a torque. So you have a propeller and I push it here. What happens? It rotates, right? The center of mass of the system is stationary, right? But the mass is rotating. When there is rotational equilibrium, right, then the angular moment of the body is a constant. When there's translational equilibrium, the linear momentum is constant. When there's rotational equilibrium, the angular momentum is a constant. So if you push it, right, at that moment, there is a balance of forces, but there is a brief torque given. That brief torque leads to it to start rotating. Okay. Now, if that torque is to be negated, or that, and if nothing happened, it will keep on rotating. Okay. Because it has a now acquired a constant angular momentum, and if there is no external torque, that will keep on rotating. Okay. So keep that in mind. Now, if dl by dt, what is L? L is angular momentum. What is angular momentum? I, the moment of inertia times omega. What is omega? Angular velocity, right? So if dl by dt equals 0, it means there is no torque. Okay, and if there is no torque, we say there is rotational equilibrium. If there is a torque, what happens, right? Let us say I am continuously pushing, right? It will go faster and faster and faster and faster and faster, because there is a continuous torque. It's going to go faster and faster and faster and faster and faster, right? L equals I omega dl by dt, therefore equals I times d omega by dt, and d omega by dt is alpha. Omega is what? Angular velocity. D omega by dt is angular acceleration alpha. So tau equals I alpha. If there is no tau, then there is the angular momentum stays constant. This is the rotational equilibrium equation of Newton's first law, second law, right? Rotational equilibrium equation of Newton's first and second law. Okay, so keep that in mind. Okay, so they are very equivalent ideas. Now, a couple is two forces that act at different points but have the same value. Okay, now a couple, what does a couple do? So if you had a positive charge and a negative charge, and you had in a electric field, they would experience a couple. Okay, then you have what is called the, like you will have P cross E representing the torque experienced. Okay, similarly, if you had a just a straight body, and you had AB, and you had a two forces F and minus F, the moment of the couple will be R cross minus F, R1 cross minus F plus R2 cross F, and therefore you will have R2 minus R1 cross F. R2 minus R1 is AB. So R2 minus R1 is the, this is independent of the point about which you are calculating the momentum. So the moment of a couple is independent of the choice of origin. Okay, couple is two forces equal and opposite acting on the same body. Okay, so you spin it, it's going to have the moment of the couple is what? The torque. Okay, torque of two equal and opposite forces. Okay, now in a lever, right, you works on the principle of moments. Okay, now if there are two unequal forces, they have to be balanced by keeping the distance proportionately different. So what does a lever do? Lever has a, there is a first order lever, second order lever, third order lever, right? A lever provides you mechanical advantage. On this side, you apply less force, right? Let's say you had a lever like that, you wanted to move a heavy stone, right? On this side, you apply a lesser force, and it, on this side you have a, you move it just a little bit. Okay, so um, so using that, you end up with a lever. Now the small force, you can then hold up a heavy body. So if you had a this kind of a what do you say, let's say a seesaw. Okay, this seesaw, this is the pivot, and on this side you have F1, this side you have F2, and F2 and F1 are unequal, but F1 D1 R cross F about the point O, F1 D1 if equals F2 D2, the system will be at rest. So the net force or the net torque will be R1 F1 minus R2 F2. Okay, therefore you end up with this net torque, and therefore the mechanical advantage is d2 by d1 or f1 by f2. Okay, so the center of gravity of a body is the point on the body where the torque due to gravity or gravitational torque is equal to 0. The uniform gravitational field, center of gravity and center of mass both coincide. right? So now here's another example. Okay, so W1 plus W now equals K1 plus K2. Okay, so and at K1 and K2 there are two torques, R1 and R2. Now W1 plus W equals R1 plus R2, where R1 and R2 are the reactions at K1 and K2. So now if you take moments about the center of gravity, then if you take moments about the center of gravity, what is the torque due to the weight itself? It is R cross F, but R is 0, right? What is the torque from this one? It is PG times W1, right? PG or right, GP times W1, GP times W1, right, is towards me, so it is considered positive. Okay, now G K1 times R1, but that is that way, right? So GK1 times R1, therefore that is inward, therefore it is negative, right? Because R1 is in the other direction. This force is in this direction, right? So now, what about the third one? Third one is like this, right? GK2 times R2. GK2 times R2. So it is outward, therefore positive. So the sum of these three torques due to W1, R1, and R2, the sum of those torques will also be zero because the body is at rest, rotational equilibrium, right? So you end up with two equations and two unknowns. What are the two unknowns? R1 and R2. Okay, so certain problems you have to use in addition to translational equilibrium, rotational equilibrium. So rotational equilibrium as well produces a equation. The same is true about the ladder problem. In the ladder problem, the ladder experiences many forces. One is we are saying that this surface is smooth, but this surface is rough. And as a result, on this side, there is a N2, normal force. On this side, also there is an N1, but there is also a F, static friction. And these three come together along, and then there is mg, right? So you have 1, 2, and 3. Remember that static friction is an unknown, right? You have as much as you cannot use mu n here. Okay, static friction is an unknown, so they will try to trick you with that. Okay, so in this kind of problem, the ladder kind of problem, you have to use moments. There are multiple forces acting at multiple points. You do have to use moments. Sometimes even in a brick problem, you will have to use moments like that when there is friction. Okay, when will the brick rotate, etc. Okay, or that will also produce you a extra equation. Sometimes you have to know when you have to use use that. Okay, so now you have uh, three sets of equations. One is forces in the horizontal direction, forces in the vertical direction, and finally forces torque about one of the axes. Now when you take torque, as I said in last class, you take it about a point about which there are a lot of forces. So then you just have, now in this case, because this force is smooth, this ball is smooth, just have mg and n2. Okay, so firstly, F is equal to N2. So that produces one equation. Now in this direction, right, in the Y direction, N1, right, equals Mg. Okay, so you now have these two equations, right? But then you have three unknowns, 1, 2, 3. Now the third equation is produced by taking torque about B, right? So if you take torque about B, you have N2 times AD, or if the length of the is L and it is at an angle theta, L cos theta will give you for N2 times L sine theta, right? L sine theta is going to give you AD, right? N2 times L sine theta. What's the direction? N2 R cross F. So outward. Okay, now if this is outward, now what about mg, right? So mg times cos theta, and mg is halfway there, right? So you have mg times L2 cos theta. Okay, and that is inward, right? So mg times L2 cos theta minus n2 L sin theta equals 0. But you already know that n2 equals f. So n2 equals f equals mg cos theta by 2. Okay, so now you've solved two of the unknowns. The third unknown is already solved, and one equals mg, right? So from these three, you've solved for all three equations. What is the net force? N and combination of n and f, right? The net force at the bottom is the combination of n and f. So you have square root of n1 square plus f square that you can calculate, and n2 equals f, right? Therefore, from that you can calculate. Therefore, you get mg square root of 4 plus cot square theta. Okay. So block plays on inclined plane, as I said, when there is friction, you can have a third equation with respect to torque. And in this case, you see he has got nx, the normal force times mg cos theta, right, equals f times h by 2. H by 2 is this. So he's taking moments about this point. So F times H by 2 equals N times mg, N times x. Okay. So what is x? X is this distance. Okay. This distance. Friction happens here, right? Therefore, you end up with this distance. He's taking moments about the point C. So N times x, right? N times x equals f times h2. All right. So when you use that equation, you then end up with the inclined plane problem solved. Okay. So now I'm going to discuss. This was what you did last class, right? And I'm now going to discuss the quickly moment of inertia. Okay. So let me switch slides. All right. So moment of inertia is basically the constant that you multiply to produce the angular momentum. I times omega. What is that? I is the moment of inertia. Okay. So so let's now look at how moment of inertia is derived. Right? Last class itself, I got into this, right? Half mr square, right? Now, if you had a rotating body, the each of the particles in the rotating body end up having a kinetic energy, right? And therefore, the sum of all those kinetic half mv squares will produce you the total kinetic energy. But then if you look at the V equals R omega, so then you have mi omega Ri square. So then you take the omega square outside. So then you have the remaining is half mi Ri square, right? That will give you the sigma mi Ri square is effectively called, this term sigma mi Ri square is called I, or the moment of inertia. Sigma mi Ri square is called moment of inertia. Okay. So now it can be thought as the analog of mass from linear dynamics in rotational dynamics. Notice the dimension. Okay, ml square. Right? Sigma mi Ri square. Therefore, it is ml square. Right? So kg meter square. Right? Usually denoted by I. So kinetic energy is half I omega square, and angular momentum is I times omega, right? Now, if you say L equals I times omega dl by dt, which is torque, equals I alpha. Now, it does not depend on the angular velocity, mass, shape, and size of the object. It depends on mass, size, and shape and size, but on all three. Okay, it is a characteristic of the rigid body and the axis about which it rotates. So you'll have different moment of inertia based on the axis about which you calculate the moment of inertia. So it is a measure of inertia in rotational motion. Okay, so now if you had a thin circular ring, you have all you just do sigma mi ri square. All the r's are constant. If you just take out the r's and you have r square sigma mi. Sigma mi is m, so mr square. Very simple. Okay, for a thin circular ring because the lengths are the same. Now three particles arranged like this, you do individual sigma mr square. So about some axis, right? About this axis, this one is 0. This one has m2 is m, and the length is l by 2, right? And this or a by 2, right? So each side is a, therefore this is a by 2. This is also a by 2. Therefore you have 2 times m times a by 2 the whole square. Therefore you end up with ma square by 2. Okay. So now if you had a rod right about it the middle, you will then find that it is m times, so for this rod, right, m times l by 2 whole square plus, right, so this is about which point? About the center. Okay, so each of the thing is half m and half n, right? Massless, you know so mass is fixed at the ends of a massless rod. Both masses are equal to m. Okay, so each mass has an m times l by 2 the whole square, mr square, right? There's a, so the rod is massless. There's a mass here of m, mass here of m, right? So now m times l by 2 the whole square plus m times l by 2 the whole square, ml square by 2. If you had a uniform rod and you were taking the moment of inertia, about one of the ends, right? And you then have to do dx, right? Dx equals rho m equals l rho d the dm equals rho dx, right? And therefore you have x square rho dx integral, right, 0 to l. So you have to r square dm, integrate that. Okay, to r square dm, integral r square dm is the moment of inertia. So you have 0 to l, from here to here, 0 to l, you for each of the little dx's, right, you have rho dx as the mass, r square, and the r square is x square, right? So the distance is x, so x square times rho dx. Rho dx is n. So x square dx is x cubed by 3, 0 to L. Therefore, you have ml square by 3 about one edge. Now, you then, if you did it about this point, some point in the middle, you'll find that it is ml square by 12. And again, it's a integration. Okay, you do integration minus L by 2 to plus L by 2 r square dm. Okay, and rho dx, same thing you do. Okay, then you will find that it is ml square by 12. Okay, now if you have a uniform circular disk, it is, how do you do that? At a distance r, what is the area? Area is the length 2 pi r times dr, right? So rho rho a, what is a? Pi r square. M equals rho times pi r square, right? Rho is what? The area density, right? So pi r square times rho equals m, right? So now dA is what? So at a distance r, dA is what? 2 pi r dr. So you have a thing, something of thickness dr, and the length is 2 pi r. 2 pi r dr will give you dA. Okay, so rho times dA, right, will give you dm. So r square is what? R is what? R square. R square is just r square. R square times 2 pi r dr times rho. Okay, r square 2 pi r dr. This is at a distance, given distance r, thin ring. So its moment of inertia, as you know, is mr square, right? So 2 pi r dr times rho will give you the m, and the r is r square. So now you integrate all those di's, you end up with I. So 0 to r. So 0 to r, you do that integral of the di. So 2 pi rho you take out. So r cubed dr is r power 4 by 4, right? And r power 4 by 4, you end up with, well, the 1, 2 will cancel, and therefore you'll have mr square by 2. Okay, and so you use that to calculate. Okay, so now a hollow cylinder, similarly, mr square, etc. Okay, now if you have a uniform solid sphere, you do a similar integration, but in this case, because it's a solid, you do 4 pi r square dr. 4 pi r square dr is the volume of a spherical surface. 4 pi r square is the surface area. Surface area times the thickness. Thickness is dr. Okay, and therefore 0 to r, 4 pi r square dr times rho times r square. Very similar to the uniform circular disk. There you had 2 pi r, right? The length of the circumference 2 pi r. Like that, the surface area of a sphere is 4 pi r square. So 4 pi r square dr. Therefore, when you do the integration, 3mr square by 5. Now, there is this thing called radius of gyration. Radius of gyration is the value k such that you end up with mk square as the moment of inertia. So if you had 3mr square by 5, right? What is the value of? So how can you make it right? K is the radius of gyration, right? What is the k? So it is of the form something times L, right? So in this case, you take out the, you have 3r square by 5. Therefore, it will become root of 3 by 5 times r. The radius of gyration, root of 3 by root of 5 times r. You take the mass out, everything that remains is k square, mk square. For a I equals mk square. What remains? So you take the m out, you have 3r square. Therefore, you take the square root of that, you have root 3 by root 5 times r. That will be your radius of gyration for a uniform sphere. This will have a different radius of gyration. This will have a different radius of gyration. That's what we are trying to explain. Now, there are two theorems. The first I want to explain is this one, a parallel axis theorem. So now I need a tool to explain this. Here, assume this is a uniform rod. Okay, so now what it takes to make this spin versus what it takes to make this spin, as you know, is different, right? So about this point, it is ml square by 3. About this point, it is ml square by 12. So the least is about the center of mass. Where is the center of mass? Here, right? So about this point, so the least moment of inertia is about the center of mass. So about any other axis, so let's say we had it about this point and you made it rotate like this, it'll take you more energy. Okay. If you have made it rotate like this, it takes less energy. If you made it rotate like this, it takes more energy, right? So about the center of mass, you have the least moment of inertia. Okay. And so we already calculated for a rod the moment of inertia as ml square by 12 about the center of mass. Now, to about any other axis, you just have to take that and do ma square, where a is the distance between the current center of current moment of inertia and about the center of mass and this one. Okay, and then you can then go from there. Okay. Now there is another theorem which is called the perpendicular axis theorem. So perpendicular axis theorem says that if you had an ix and an iy, right, the sum of the ix and the sum of the iy will equal iz, where x, y, and z are orthogonal to each other or perpendicular to each other. So ix plus iy will equal iz, where which is z, which is x and y, where x and y are on the plane of the of the planar body. Notice this is only for only applicable to planar object, that is a plate or something like that, square board, square thing, or a plate. Okay, so if you needed to find about one of these axes, right, versus about this axis, you can correspondingly find it. So if you had a square body, right, and you had I gave you the moment about Iz, and you had an Ix and an Iy, which is in this direction. Will they be equal to this direction and this direction? Is this direction plus this direction equal to this direction and this direction? Well, yes. Okay, that's the very surprising result, but that is also true. Okay, so with that, I'm going to stop. So this is the simple example I gave you: ml square by 12 plus m times l by 2 the whole square, right? Therefore you have ml square by 3, right? So this is roughly the material associated with moment of inertia. We will do a few problems next time with involving some of these rotational ideas, okay? And then we'll wind down rotation and then move on to the next set of ideas, which will be simple harmonic motion. Okay, so we'll do some problems and then we'll move on to simple harmonic motion in the next class. So until then, I'm going to bid you goodbye, and then we will meet again next class. Today was a little bit short in class, but I hope you did understand what moment of inertia is about and all the rules involved, and try some problems with moment of inertia. Always helps to solve these problems and understand these two theorems: perpendicular axis theorem and parallel axis theorem. Parallel axis theorem, remember, is about the center of mass is the lowest, and about any axis, you do m plus m a square. All right. So with that, I'm going to stop and we'll continue again next class. Okay. So thank you very much.